Hello everyone! In this video we will continue to examine topic 5.2, the heating effect of electric currents, and in particular we will continue to focus on Kirchhoff's circuit laws and in particular potential and potential difference. Alright, so big mystery. If the current stays the same before and after a resistor, then what does happen in the resistor? So as we think about sort of the basic circuit that gave rise to our considerations for Kirchhoff's first law, there's an instinct we have that something must be happening, something must be giving away something at the resistor, right? And so we've just discovered that it's not current. The current doesn't drop. But what does happen is that the energy per unit charge drops there. So the charges lose energy at the lamp. And in fact, they deliver energy to the lamp in the form of thermal energy and ultimately light. So question, if the charges lose energy and therefore sort of conceptually slow down, I'm going to put that in quotes because they don't actually slow down for some complex reasons. Happy to answer that later if you'd like. But if they sort of slow down, quote unquote, shouldn't the current drop? And the answer is no, because the rate of the charge flow doesn't change. So if I use a metaphor here, right, imagine that sort of electric current is a lot like water current. It's like water flow inside a pipe, all right? And then here's our metaphor. If the water is sort of going through a small opening here, it's going to be moving at sort of high velocity. And you can imagine the resistor, the lamp, is like a little fan or turbine or something in the way of the water. So when the water hits the fan, it does, in fact, slow down, and it loses kinetic energy. But what happens is that the total water in this front end is going to be, the total water in any unit of time through this front end is going to be the same as the total water out of this sort of fat back end. It's just that this water will be moving slower as it has delivered energy to the turbine or the fan. Fundamentally, saying that the current in is equal to the current out is just looking at delta Q per delta T, right? It's the total rate of flow in and out. Even if the energy has dropped off, that flow in to this pipe is going to be exactly the same as the flow out of this pipe. Otherwise, you would end up with vacuum or air bubbles or something going on here because water is basically incompressible. It can't be pushed into itself. And this is a pretty good metaphor for what's going on with electric current, that as electric current sort of goes into a resistor, it gives energy away or delivers energy to the resistor, but the same rate of charge flow is maintained throughout the total length of the resistor and, in fact, after the resistor.